All right, so ready? We're going to show it for the first three terms. So part one. All right, does 1 cube equal 1 times 1 plus 1 over 2 squared? Well, last I checked, 1 plus 1 is 2. 2 is canceling it with 1. Check. Does 1 cubed plus 2 cubed equal 2 times 2 plus 1 over 2 squared? Well, let's look. 1 plus 8 is 9. So let's see what happens here. These 2's cancel. 2 plus 1 is 3. 3 squared is 9. Well, hallelujah. We're going to do it for a third one. What I'm doing, you may say, Ripley, you're being pedantic. I don't want to have to do this. Well, trust me. What we're doing is we're just building an understanding that it appears that we can roll through this thing, but we don't know what happens further on down the road. So what is that? Oh, goodness. What's that going to be? It's going to be 27 plus 8 is 35 plus 1 is 36. So let's see. This is going to be 3 times 3 plus 1 all over 2 squared. Well, 3 plus 1 is 4. 4 divided by 2 is 2. 3 times 2 is 6. 6 squared is 36. Outstanding. Nice. All right, so here it comes. Here's the part that gives everybody fits. But you can't think of this thing as standalone. It works in combination with part 3. So part 2 simply says, suppose that 1 cubed plus 2 cubed plus 3 cubed plus ... plus k cubed equals k times k plus 1 all over 2 squared. Now, why do we have to put a k in there instead of an n? What's the right word? It's a semantic issue. We don't want to suppose the thing that we're trying to prove. Okay, so think of it this way. N is any number n. So any number, all the way out to the biggest number that you can think of, and then add 1 to that, and then multiply that times a Google, and then go from there. What we're saying is k is fixed. K is some fixed number that we stop at. Now, it can be a monstrously huge number, but we're not saying that this is working broadly for all numbers. We're saying, okay, let's fix a k, and then we're going to assume that it works for k. We're supposing that it does. Now, part 3 is show that 1 cubed plus 2 cubed plus 3 cubed plus ... plus k cubed plus k plus 1 cubed is equal to k plus 1 times k plus 1, which is k plus 2, all over 2 squared. Show that it works for the k plus first term. That's very key, that we understand that these two steps work in combination with one another. Suppose this, suppose 2, prove 3. Well, again, I'll change colors again. Watch what happens. Pretty simple. I see a 1 cubed plus 2 cubed plus 3 cubed plus ... plus k cubed. Guess what? I'm allowed to assume that that equals that because I'm supposing it. Again, my supposition may be incorrect, which will play itself out algebraically in this. We know it isn't because we know that this is the equation. But we're allowed to at least assume it and see what happens in so doing. So here we go. I'm going to have k times k plus 1 all over 2 squared equals plus k plus 1 cubed. All right, and then we'll throw a little question mark in here because I don't know if they're equal yet. Okay, so here we go. Same thing. I'm going to find myself a common denominator. I'm going to leave this as k. I'm actually going to simplify my fraction here just a little bit. This is going to turn into k squared and then k plus 1 squared all over 4, which implies when I find my common denominator, I'm going to have a plus 4 times k plus 1 cubed all over 4. So I can just write this as a big old common denominator. Now again, look at that. Same sort of trick. I see that this has a k plus 1 squared. I see that this has a k plus 1 cubed. So I can factor out a k plus 1 squared, can't I? Now look, if you keep your eye on the prize and you think about this, this is really k plus 1 squared times k plus 2 squared all over 2. So I've sort of done the heavy lifting so far. watch what happens. If I factored a k plus 1 squared out of both of these terms, I'm left with a k squared plus 4 times k plus 1 all over 4, which equals, excuse me, I'm coming up this way. If I look, I get k plus 1 squared times k squared plus 4k plus 4, and your spidey sense better be tingling, all over 4. K squared plus 4k plus 4 is just k plus 2 squared, so this is k plus 1 squared times k plus 2 squared, all over, think of 4 not as being 4, but as being 2 squared, and guess what? We end up with k plus 1 times k plus 2 all over 2, and everything is squared. QED. Isn't that awesome? It's very cool. It's also really, really useful mathematically. We use the bejesus out of that thing in mathematics. Okay? Well, let's do one more that's not quite as straightforward. What's a good one? I'm going to do, let's do, how about this guy? Prove, wow, a little twitch there at the end of that guy, didn't I? Prove, sorry, n squared plus n is divisible by 2, where n is in the positive integers. All right? All right, so ready? Same thing. Let's see what happens. Part 1. We're going to show it works for 1. We're going to show it works for 2. We're going to show it works for 3, etc., etc. Now, there are lots of ways to prove this. I'm not saying that mathematical induction is the only way, but by God, it sure is elegant, and it sure is clever the way it works out. So, are you ready? All right, for n equals 1. Well, let's see. That's 1 squared plus 1, which is 2. Check. It's divisible by 2. N equals 2. Well, that's pretty easy, right? 2 squared plus 2 is 6. Check. N equals 3. That's going to be 3 squared plus 3, which is 9 plus 3, which is 12. Check. Part 2, the inductive hypothesis. Again, it doesn't exist in a vacuum. It's working with part 3, okay? So suppose that k squared plus k is div by 2. And I'm going to write in here for some k. For some fixed k. So you fix k, you hand it to me, and I'm going to show you, so k is in the positive integers. You're going to hand it to me, and you're going to say, okay, if I square it and add it to itself, then I end up with a number that's divisible by 2. And then part 3 is show what? K plus 1 squared plus k plus 1 is div by 2. Oops, I don't know where I got dived from. Is divisible by 2. Same basic principle. Watch. I'm just going to look for a k squared plus k. So I don't see a k squared plus k. I see a k plus 1 squared, and I see a k. That's not going to do me any good. However, if I look close, look, doesn't this imply that I get k squared plus 2k plus 1 plus k plus 1, right? Well, remember, I'm looking for a k squared plus k. So this is k squared plus, I'm going to steal that k, I'm going to borrow that k for a second, plus k plus 2k plus 2 if I combine my 1's. Now, by the inductive hypothesis, this is divisible by 2. Check this guy out. Clearly divisible by 2. Since the sum of, oh wow, come on Ripley, let's finish it up on the second page. That's just going to be too ugly. Since the sum of 2 terms div by 2 is also divisible by 2. Think of it as factoring out a 2. Also div by 2. We have shown or showed that k plus 1 squared plus k plus 1 is div by 2. QED. Awesome. Now, I want you to try one on your own. This one's very clever. I want you to try this one. I want you to prove that, let's go 3 to the n minus 1 is even, which you can think of even as being div by 2. Now, try it on your own. See if you can go through the inductive steps to show that it works, okay? And then I'll meet you back here in just a sec, and we'll just hit pause on your thing, see if you could do it, and then we'll check it. We'll do it together, okay? Give it a shot. Okay, so let's see what happens. Part 1. All right, n equals 1. I got 3 to the 1 minus 1 equals 2. Check. It's even. N equals 2. 3 squared minus 1 equals 8. Check. N equals 3. 3 cubed minus 1 equals 26. Check. Perfect. Part 2. Now, what do we do? Suppose 3 to the k minus 1 is even for some k. For some k. And in combination with 3, show 3 to the k plus 1 minus 1 is even. That's what we have to show. That's our job. All right? So how do we do it? Well, I need a 3 to the k minus 1 to be able to use the inductive hypothesis. The problem is I have a 3 to the k, right? I'm going to do a really clever little trick here. Watch this. I'm going to turn this into 3 to the k times 3 minus 1. Now, this isn't quite yet a 3 to the k minus 1 because this 3 to the k is attached to this 3 right here. But watch. Here's the big trick. What if I were to do this? What if I were to go 3 to the k times 3 minus 1? Now, the problem is that this 3 is multiplicatively attached, so I got to figure out a way to get rid of the 3 by factoring out. So I have to manufacture another 3. And the way that I do that is I'm going to subtract 2. But I can't just subtract 2. I got to add 2 as well, because remember, you can add 0 whenever you want. And negative 2 plus 2 is 0. So watch what happens. This equals 3 to the k times 3 minus 3 plus 2. This, if you notice right here, this term, this guy right here, has a 3. I can factor that 3, not 3 to the k, but it's got a 3 sitting there. Watch what happens when I factor out that 3. I get 3 times 3 to the k minus 1, and then plus 2. Now, that's kind of like, oh, we're there, because I know that that term is divisible by 2. I know that 2 is divisible by 2, and then this 3 is just along for the ride. If I've got any term in a product that's divisible by 2, the whole thing is divisible by 2. So really, whoops, not that part. This whole statement, I'm just going to borrow this statement, send it over to the other page, and we showed, wow, this thing's lagging today, showed 3 to the k plus 1 minus 1 is divisible by 2, or even. Yeah, QED. It's cool stuff. Hope you like it. It's going to wrap your brain in a twist for some of it, but it's definitely fun to play with. All right? Thanks for your time and attention. We'll play a whole lot more with these in class. So have a really good day, and I'll see you tomorrow. Bye-bye.